My name is Bartelt, and I've been working for the last 30 years in the field of the simulation of mass movements. What we've done in Switzerland is we've developed a program that we call RAMS that we use in practice at the universities as well as for government agencies to simulate mass movements. We're pretty much used everywhere in the world. We're used in high mountain regions, cold regions, and also, of course, within the European Alps. So the first question that you might have, if I could, is what does RAMS mean? And RAMS is it stands for Rapid Mass Movement Simulation, and we just shortened the title to this acronym. RAMS is not one program. RAMS is a series of programs that we use to simulate snow avalanches, which was our first activity, but also debris flows, rock falls, GLOFCs, and increasingly now rock ice avalanches. RAMS simulates movements from initiation to run out, and I've tried to show this here. This is a snow avalanche simulation, and you see that we define the starting zone, and our goal with RAMS is to find how the flow moves in true three-dimensional terrain, primarily the run-out distances of the flow, or also the velocities and the impact pressures. RAMS is used throughout the world, primarily for hazard mapping, but also to set up warning systems, and also increasingly the design of mitigation structures, such as rockfall dams, avalanche dams, debris flow mitigation measures, and also rockfall mitigation measures. RAMS we're not based in Zurich. Today I'm in Zurich, it's very hot. I'm in the spring. The RAMS team is based in Davos, Switzerland. It has about 5 people. We're a collection of engineers, we're a collection of physicists, experimental physicists, geophysicists, and we all work together to produce one program. Just to show you where we're located and also what our institute looks like in the winter. As I said, RAMS is not a generic simulation program. It's not one simple program. We have special modules that take into account the specialities of each process. We have a module for snow avalanches. We have a module for debris flows, a module for rock falls, and now a new model for the rock ice avalanches. What we have found is that it is basically impossible to simulate these different processes with a single program. So each one has to take into account certain effects. For example, in the snow avalanches, it's the material snow or the temperature. Debris flows, you have to take into account sediment entrainment or how water lubricates the flow. Rockfall, of course, is completely different because it's a discrete process, but also rock ice avalanches. We have to take into account rock, how ice melts in a rock ice avalanches, and how you have different type of transformations. So in each one of these modules, what we've managed to do is to develop sets of parameters that we can use immediately to simulate an event. So we've had a lot of experience over the last 20 years, and we've tried to take each module, or tried to gain as much experience as we possibly can to develop parameters that the engineers can use as a first approximation of the problem. So when you're using RAMS, you'll now see this, but what's behind it, there's a lot of software engineering, and this software engineering is basically decomposed into 2 parts. There's a computational core, and the computational core is C++, and this is where we set up systems of equations and we solve them numerically, and a graphical user interface. And the graphical user interface is shown here on the slide, and we use the IDL system, and this gives us the ability to set up problems with ease. We can set initial parameters, we can set different release zones in different areas. We have the entire ability to define, for example, the three-dimensional topography, different boundary conditions, different friction parameters in that terrain. So we've done a lot of effort to make it possible to solve problems as quickly as possible, with the goal that the users can set up scenarios. It's very unusual that you have a one problem and you know everything. Typically, when you use RAMs, what you want to do is you want to test different ideas out, different locations of starting zones, different volumes of starting zones, different entrainment characteristics, and so forth. So that's extremely important, that you are able then to set up problems easily, get the results, see what they are, and then do different types of scenarios. Behind everything in the RAM software is a digital elevation module. You can't do RAM simulations without an accurate elevation module. We use these for, they represent the three-dimensional terrain. The resolution, I'll talk about that quickly now in the next slide, but the resolution depends upon the process. For example, if you're doing small avalanches, then you need a high resolution DEM. If you're doing GLOFs, then you can use lower resolution, or much coarser resolutions. And all of the modules, all of the processes are based on the problem or our abilities to have good digital elevation modules. I want to move this out of the way. I put here, I put here, snow avalanches, we typically use 2 to 10 meter resolution. And you see for the GLOFs, I think that we can do good simulations going up to 10 to 20 meters resolution size. So as I said, the resolution of the DEM that you use in RAMs depends upon primarily the size of the event that you're trying to model, or the volume of the event that you're trying to model. Input and out features, what we have found in engineering practice is that the geographers and the engineers, they want to work with with a lot of GIS type features. They want to have maps of the terrain. They want to superimpose simulation results on those maps, on those ortho photos, in order to make comparisons to see directly how good the results are. So we've done a lot of work in implementing a lot of GIS type features into the RAM software. At the same time, it's also possible to transfer the data to the GIS programs to do higher order analysis with it. So there's a lot of features, for example, transparencies, contour lines, plots, profiles, hydrographs, shape files that you can use to set releases and stuff like that. So I'm looking forward to coming in June and to show you exactly how that works. Now, now we're going to go make a step towards the physical problem. RAMs is the modules, we divide them into flow models and particle modules. The rockfall model is a particle model. And by that I mean is that we model each individual rock as it hits the ground, each individual discrete event. The rockfall module is the rocks bounce and they hit the ground and they slide and they roll, etc. We call this a mechanically non-smooth system. The other modules, and the one that you'll be working with to simulate GLOFs, are what we call a flow model. Here, we do not model every single particle. It would simply be impossible. We cannot model millions and millions and millions of particles and expect to get any kind of reasonable result. So what we do is we use continuum systems. We model the particle interactions, the interactions between rocks, between snow granules, and the water, how water interacts with these processes, and we treat it as a mechanically smooth system. So the module that you're going to be working with is a continuum model. Of that is that you can do simulations very, very quickly and get very good results. So it's important that you know this distinction. For us, what has been very valuable has been to understand the particle interactions that go on during these flows, the interactions between snow granules, rock granules, because that has taught us a tremendous amount about how these things work. So just to give you an idea of what the rockfall simulation looks like, so this is a model where you're taking into account the individual particles. This is a rock slide that we were simulating above a railway line, trying to determine what the effectiveness of a rockfall dam would be. As you see, what we found out is that you cannot simulate these things, or a rock slide or rockfall, without taking into account the particle sizes, taking into account the block shape and things like that. So yeah, that's basically the way that we solve the rock fall problem right now. Another thing is that, of course, the interactions with the ground, because we have to take into account each discrete particle interaction with the ground, we've developed special purpose algorithms to find out how the rocks, when they are rotating with different shapes, how they interact with the ground, and how much energy basically they lose. The RAMS rockfall module is, for me, extremely important because we've done a lot of experimental work. All of the RAMS modules are backed up by experiments. That is, we go out into the field and we actually drop rocks down slopes, measure how far they go, how fast they rotate, in order to determine the parameters that the engineers need to be able to calculate these types of mass movements with accuracy. Another example, one of the problems that we're working on now in the rockfall module is that we not only treat individual trajectories, but we also have statistical modules that allow you then to do a statistical analysis. That is, one rockfall trajectory is simply not enough to be able to judge the hazard in a particular region, and therefore we are combining this type of module with statistical methods in order to come up with an overall hazard assessment. And finally, another important part of the rockfall problem that we're working on in the RAMS rockfall team is the influence of forests. Rockfall is a problem that is extremely, where the forest has a very large protective effect, and we are actively involved in experiments in the field in trying to develop methods that accurately state how the forest can predict, how the forest can successfully hold back rocks and protect streets and buildings. This is a big problem in Switzerland, and this is perhaps a little bit different from the other modules that we have to get so detailed information about the forest. So going on to the next module, so we're going to take a jump now. We're going to the flow model. The first flow model that we developed was the avalanche module. The avalanche module has been used in practice since 2010. We've developed different methods to simulate avalanches over that time. The one that we're now using takes into account the fact that the avalanche has a granular core of snow clods, and as well as a powder cloud, and therefore we're able to not only predict the motion of the granular core, but also the air blast of the cloud. This has happened in many regions in the Himalayas where you have large rock ice avalanches, and the destruction that they cause is caused by the air blast. And we found that this is to be an extremely important part of developing an overall hazard assessment. All of the flow modules, the one that you're going to be using in the debris flow, as well as the avalanche debris flow and the rock ice, they are all based on what we call shallow water equations. The shallow water equations are depth average, meaning that you obtain over time in three-dimensional terrain the flow height as well as the flow velocity of the material that is moving. These are the basic equations shown below that we that we apply. We have models that make simple assumptions concerning the flow density, but we also have models that make more complicated assumptions. For example, the formation of the powder cloud, and et cetera, et cetera. So we feel very confident that we can work at different levels. We can solve the problem with simple models, but we can also go into situations where more complicated models are necessary. Here is an example. This is a hazard assessment of a snow avalanche here in Switzerland. This is what a powder avalanche simulation looks like with the RAM software. You see in the colors the motion of the core, and outside in the gray region you see the air blast. All of the models that we apply for the flow are based on these foamy friction type models. Fermi was a Swiss engineer who was working in the 50s, and he developed a very simple 2-parameter friction model that we apply in snow avalanches, debris flows, GLOFs, and rock avalanches. And this is the basic equation. It consists of 2 parts. It consists of a Coulomb friction, and it's given by the parameter mu, and it consists of a velocity square dependent resistance or friction, and it is divided by the parameter c. The division causes sometimes problems because the higher the c, the lower the friction. But it is basically this 2-parameter model that we will be using as a first step to simulate GLOFs. Now, this 2-parameter model has, in its simple form, a lot of advantages. One of them is it's simple to use, and we know what parameters are realistic. The parameter mu controls the runout distance, and the parameter c controls the velocity of the flow. So with 2 parameters, we can pretty much control the whole event. Now, when we turn to more complicated models in RAMs, we then make these 2 parameters functions of different processes. For example, different amounts of water in the flow, different amounts of granularity or sediment type. So we have we use simple models, we can use complicated models. Each one has their advantages, but we have a pretty good idea of what these parameters should be and what the realistic sets of friction are for certain types of flows. And when we get into trouble, then we can go to more complicated models. For example, if we have scenarios with different amounts of water, then we know we have a pretty good idea of how to change them over time, or how to change them. To come to the debris flow module, this is the one that you'll be using. We have here a single phase model. I think the advantage of this is that it's very quick. We have 2 types of, we can simulate very long debris flow channels, at least several kilometers long in reasonable amounts of time. We have 2 different types of release zones that we can define. We can define a dam release, sort of a block of mass that is then released at some point on the mountainside, or we can define hydrographs. Hydrographs are becoming extremely popular. A lot of people like working with discharges and volumes to define the debris flow scenarios on for a particular torrent. The debris flow module has another important part to it, and that is that it's possible to include entrainment. Our institute over the last 10 years has done a tremendous amount of work on trying to quantify how much a debris flow entrains over time. We have then developed a model based on the experiments and the observations that we apply to simulate the growth of a debris flow over time. And this turns out to be very, very important when doing hazard analysis, being able to come up with predictions of how a mass flow increases in size dependent upon the properties of the torrent. The model requires that you state what the maximum depth of erosion could be. This is typical for us because we have sediments lying on bedrock, and we have a pretty good idea of what the maximum depth of erosion is. We then need to take a look at the sediment and see what kind of critical shear stress, that is the shear stress that will be mobilized, at what stage then, what size of a debris flow has to occur such that we have large entrainment rates into the debris flow. And then we have to have another parameter that states how quickly can we entrain that mass over time. Is it very, very solid mass, very strong sediments that we are not able to entrain very quickly, or meaning that the growth of the debris flow is very slow, or are we putting all of the mass immediately into the front of the debris flow over time? So coming in June, I think one of the problems that we are going to have to talk about with all of the people in the audience is how are we going to handle this type of entrainment for your systems. Perhaps going back a little bit, one of the features of the debris flow problem is that for our studies where we're talking about debris flows of maybe 20,000 to 100,000 cubic, which are probably much, much smaller than the debris flows or the GLOFs that you will encounter, we require high resolution DEMs. So this is a restriction. As soon as you get into any type of entrainment, as soon as you have entrainment problems, or if you have smaller torrents, then you need a higher resolution DEM. What we also have now, and what we're working very, very hard on, is the problem of a two-phase debris flow. What we've obviously encountered, and what everybody knows, is that the motion of the debris flow is very, very dependent upon the amount of water in the system, the amount of water entrained, the precipitation driving or causing the formation of the debris flow. So we've been working for the last few years on a generalized two-phase model that allows us to simulate the dewatering or the coupling of the solid bouldery type mass with the fluid type mass. For us, this is extremely important, such that because it enables us to see where the solid mass deposits, where we're going to get fluid washes, and also it affects greatly the entrainment processes. So it affects the relationship between the solid and the fluid mass of the size of the debris flow. So this is something that we will also be working on, or we've been working on, and we are now testing the model using our experiments. So finally, coming towards the close, what we are working on now, we've been using it for the last 5 years in Switzerland, is our rock ice avalanche module. We've been confronted in the last 5 years with many different types of large rock ice avalanches, and that we've been asked to simulate these. Probably in Switzerland, the most notable is Pizzcengolo, but also the Langtang avalanche rock ice, or ice rock avalanche, Devdaraki in Georgia, but also the Kamoli event in India. I'll show you in a few seconds what those. The problem with the rock ice, or the problem with rock ice avalanches, is that they consist of rock, bouldery mass, they consist of ice, they consist of snow, they consist of water, and therefore trying to predict how this mixture of material moves based on the different volumetric contributions over time is extremely difficult. Most of the events that we encounter involve melting of ice. So there's always this question: how much ice is melted? How much ice is entrained? And this is something that we can now simulate. For example, in the Kamoli event, this is a simulation of the Kamoli rock ice avalanche. This is I think it's about 10 to 13, 15 kilometers long. What you're seeing is the movement of the debris flow and the formation of the powder cloud. The powder cloud is also included in the rock ice model simply because we have to. There are so many cases where the damage from the cloud is caused, for example, in Langtang and different events. What we're working on now, different thermomechanical processes that we include in the model: frictional melting of ice, entrainment of water-saturated ground sediments is important, the suspension cloud. And what is extremely important is knowing what can be entrained by the event over time. And of course, when you're talking about large valleys, large regions, this can change dramatically from the upper catchment where you have maybe ice to the lower catchments where you have tremendous amounts of sediments. And we're working on getting what we call entrainment maps integrated into the model, using case studies right now to validate the model. Another ongoing activity, research activity that could be of interest to Central Asia is that because we are computationally efficient, when we use the simpler models, it is possible to simulate large regions. What you see here is a simulation of part of the Caucasus. We just recently simulated the entire Caucasus for the UN and for the country of Georgia, which contains about 2 million snow avalanches. So what we do is we couple the RAM software to disposition modules or algorithms that tell us where we could have a starting zone, and then we model all of the different starting zone in order to come up with a large-scale hazard map of a particular region. We've been doing this now for the last 3 years. We just recently completed Georgia, but we've also done the Hindu Kush in Afghanistan, large interest in regions of the Himalayan mountains, especially near Kamoli and Uttarakhand, large in Alaska, but also in Switzerland. We've been doing it for the railways as well as different cantons. So this appears to me to be something that is that is needed by many countries to get a first analysis of the number of events and the size of the problem in a particular area is how we use it. And from what we do is with it, we attempt to identify regions that are extremely dangerous, and then we zero in on those using individual analysis or more complicated or more detailed scenario analysis of the problem, including more detailed modeling. A problem that we are also encountering is the modeling of cascading processes. For example, the Pittschengelo event, it began as a rock ice avalanche. It entrained glacier ice, and then it transformed into a series of debris flows. The Kamoli rock ice event, transformed into a debris flow flood. The way that we are handling the cascading process is to couple different models together. We begin, for example, in the Pittschengelo, we simulate the rock ice avalanche. This is the simulation of this event. Here, what you're seeing in this picture is the formation of the water via frictional melting. And what you notice when you see these red regions, this is where the water has accumulated in the deposits. And we would use this information then to drive the debris flow analysis. Here we would say in this region in the deposits is where we believe the debris flows are going to start. And therefore we're going to, what we're trying to do is to perform a series of simulations, stop at a certain point where you think you have a pretty good idea that one part of the process has been correctly simulated, and then do as a second part of the process a more detailed sort of debris, or not sort of, as a debris flow analysis. So we think that the way to go in modeling cascading processes is to handle parts of the process using the specialized programs, then stopping the analysis, thinking a little bit, developing a rational scenario from that analysis, and then continuing on the second part, or so dividing the cascading process into different parts. Finally, I would like to say that RAMS is a non-profit government organization. We sell licenses to the engineering offices. We have a very large engineering community, private engineering community that uses RAMS for their hazard analysis. So we sell them, but we are also used by government authorities and universities. We would very, very much like to give our software away. We would very much like to make it open source. But here the problem is that the money that we use, it's not for profit, but it's used then to do experiments. It's used to conduct user workshops. It's used for the long-term support. A problem that we have is that we are confronted with rapid changing computer technology. It seems like every 5 years, different graphical interfaces are developed, or we have different operating systems, or we have different compilers, and therefore we continually need to make improvements and adjustments, and therefore we're sort of forced to have to generate some money. All of the money that we're using right now, to be honest, is being used in experiments in three-dimensional terrain, real-size experiments. So these are extremely valuable information that then goes back into RAMS as calibrated parameters, as better physics. And another problem that we are confronted with is that we like to keep the people who've developed RAMS around for a long time so that they can support users. It takes many, many years for people to gain experience in this whole problem, and therefore we've been able to generate financing for long-term staff. So conclusions, RAMS, it consists of 4 modules: snow avalanches, debris flows, rock falls, and rock ice avalanches. Each module consists of a specialized computational core and a specialized user interface. Every process is process specific. That is, the erosion problem, for example, the entrainment problem is different whether you're considering a snow avalanche or a debris flow or a rock ice avalanche. So we have special purpose modules that we use, and we want to use the best module for the specific problem. We have a pretty good idea of what the parameters are. So we have experience. It's not to say that we might be confronted with an event that is going to cause us to scratch our heads, but we have a pretty good idea of what these parameters are and can be used as a first scenario. What we're seeing now is a demand for larger regional scale simulations, especially to understand the role of climate change and mass movements, and we're trying to address the concerns of the climate change scientists by performing large-scale simulations. We have an idea of how to solve the cascading processes because we have these specialized modules. So there's going to be obviously more work on that in the future, and I'm very certain that in the Central Asian countries, we're going to be confronted with cascading processes. And what I think, what we're very happy about is that RAMS is strongly supported by the WSL and SLF in Switzerland, and we will be able to generate long-term support over many, many years. So with that, I conclude. I thank you for your attention, and I hope there are a few questions and that I did not speak too quickly.